Like you're so wrong. You're not. Let's put that in the business comment. It's good to say you're doing good, but. Yeah. That's it. So. Regular velocity 2.5 per second. Yeah, okay, that's what they do.
Yeah.
A naive piece of shit.
Like, yeah, so that's.
Yeah.
So this is.
I was talking about somebody about me. I think the process yesterday I was like, they're very sad. And it's like, I was
So that's. This is the. And this, J is the Y.
it's not clean.
It's either.
What do you call?
All right, guys, page 12. We briefly talked about horizontal and vertical tangents, so let me just recap that. Anytime I want to find a horizontal tangent, wherever my slope is 0, I'm always going to set the numerator of the derivative equal to 0. I mean, they say the formula is derivative equal to 0, but what that really means is if you see a numerator and denominator variable, you're setting the numerator of the derivative equal to 0. That's how you can find your horizontal tangents. Okay. Anytime I want to find a vertical tangent, basically I'm looking for a place where the slope is undefined. And that means if you see a variable in the denominator, you set the denominator variable equal to 0. That's how I can find vertical tangents. So let's practice doing that. So for number 4, it says find all horizontal tangents for this ellipse, and then find all vertical tangents for this ellipse. But first, we have to get to the derivative, right? We have to find our derivative, solve for dy dx. And once we get our derivative equation in front of us, then we can focus on, okay, what do we see in the numerator? And what do we see in the denominator? Okay, so go ahead, go through your steps to find your derivative. Remember, every variable gets its own rule. It's just that with y's, we need to attach that dy dx. So if I want to find my horizontal tangent, I'm going to focus my attention on setting the numerator equal to 0. So if I set the numerator equal to 0, what do I get? X equals 0. X equals 0. So that means we have horizontal tangents whenever x is 0. And how can I find the full locations where we have horizontal tangents?
Plug it into the original.
Original, yeah. So now we can identify the full order pairs where they are. So it's asking for horizontal tangent lines. So the order pairs will be 0, comma √8 and 0, comma -√8. But if I want horizontal tangents, then I'm going to create the equations of those lines. And my equations will be y is equal to √8 and y is equal to -√8. Okay, find all vertical tangents. So we can pick up where we left off for number 4, right? We can focus on our derivative, the same equation, right? Same derivative. But now where do we look to find vertical tangents? Yeah, so 2y equal to 0. Yeah, say that 2y equal to 0. Solve for y is equal to 0. And if I want to find the locations, I can put them back into the original equation.
So if it's just asking for the line, the y value would be enough, right?
Exactly, the y would be enough. But we would have to, well, no, these are, but it's vertical tangents though. Vertical tangents are a different equation. They have x equals as their lines.
Oh,
So y equals would be enough for horizontal tangents. But we got to solve for x for vertical tangents. So we have two vertical tangents, 4 over √3 and -4 over √3. Now, you don't have to draw the graph, but I just want to give you some perspective. This is kind of what the ellipse looks like. And then you have your y equals -√8, y equals +√8. Those form your horizontal tangents. And then x equals 4 over √3 and y equals 4 over -√3. Those are where your vertical tangents are going to be. Okay, we're just gonna see if we can go through a couple of these problems here. Pick out some of the more challenging ones so we can practice through them. Why don't we try number 3 first of all? So number 3 at the bottom of page 12. So number 3 at the bottom says sine of x plus y equals 2x. Can you identify what rules or what methods do we have to make sure we include as part of our process for number 3? Chain rule and implicit. Yeah, anytime you see y, now obviously we knew that this is under implicit differentiation because we're in this section, but we need to be able to recognize, right? You're not going to see problems where say, oh, use implicit differentiation for this equation. We need to be able to recognize the need for it. Anytime your y is mixed into the equation inside something else, something's done to that y, we know there's implicit going on. Okay, so try that. Chain rule first, and then you can activate the implicit portion. Sine's derivative is cosine. We leave the original parentheses intact. And then we have a separate space to handle the inside portion's derivative. X becomes 1, y becomes 1 dy dx. Next step, you want to get that dy dx by itself, but it's kind of stuck inside this. So you can just distribute that cosine of x plus y through, rearrange, and then eventually get that dy dx by itself.
Or can you just divide the cosine, subtract?
Yeah, you can do that too. Yeah, that works too. Yeah, we'll get the same answer. Next page. Let's get down to number 9. Page 13, number 9. Does anybody still need this? So number 9, there's some cleanup that we can do here. I mean, we can leave that square there, but we can also put that to where? In the front, yeah. And that may make it a little bit easier. Actually, it's not that big of a deal, but I just want to kind of give you the idea that if there's any properties that you can apply with logs or natural logs, sometimes that can really speed up your derivative process. But this one is just a minor thing, but it's always good whenever you see in a natural log or log expression, see what you can do before the derivative process, which could potentially speed up. So I'm going to just rewrite it. You don't have to, but now this I want to point out cosine squared x. What should we do before we do our derivative? That would be really helpful. Yeah, put a parentheses or a bracket outside as a reminder that there's a chain rule involved. Otherwise, we may miss out on the full chain rule aspect of it. Right. So now you can find the derivative. You know you have 2 y terms here. You know implicit is involved. Dy dx will show up twice. And then there's chain rule here. Outside times inside, right? Okay, go through your steps. If you need more space, use the space for number 8. We're not going to do number 8.
About natural to natural log y. Do I put the dy or dx on the outside of the fraction or just the denominator?
Right. So I would put it outside. I would say natural log of y becomes 1 over y times dy dx. That way it just doesn't feel like a complex fraction. Let me show you what I did. After this, we'll do number 11, and then we'll go to the last page. Okay, after 9, go to 11. Now, looking at 11, what's involved there if we want to find the derivative? What do we have to make sure we include? I guess a little bit of a chain because I guess implicit can be considered chain. So there's definitely implicit because we see y's all over the place. What else? Product. That's 6xy. So that's a little bit deceiving where you feel like it's not a big deal, but sometimes problems, they don't announce themselves that there's product rule here. We have to kind of recognize it. So x and y are being multiplied. They're separate variables. We have to go through product rule if we want to find the derivative. We can't just say 6x becomes 6, y becomes dy dx, and then be done with it. Now, if it was 6x plus y, then that's fine. You can treat each of them separately, but the fact that they're multiplied, we got to go through product rule for 11. Okay, if you're ahead, we're going to do 16 on page 4. And then we'll do all of last page, 20 through 22. So just number 16 on page 4.
Number 12, but for number 12, can you multiply both sides by sign to make the problem easier?
Yeah, you can. Yeah, that's what I did. I did a cross product and then I solved for the y dx.
Okay.
Yeah, get that fraction out of the way. Actually, you know what? Okay, so after this, I want to do one of the homework problems with you because I realized that I didn't spend time going over finding the second derivative implicitly. So yeah, why don't we after this, let's
59.
um Yeah, 59, but I want to do the 47 from yesterday's, from yeah, which
Put into it, right?
dydx equals.
That's equal to do y.
But we still have to go through quotient implicit to get to the second derivative, right?
Yeah.
Oh. Because this, potentially, you can solve for y due to plus or minus. That means it's going to take.
Oh, okay.
Let me go through number 11, make sure you guys are good with that. So, first, we go through power rule, right, for each of our terms. dy dx shows up for that y cube. I treat 6x like my f function, y as my g. So then we do f prime times g plus f prime, y produces dy dx. Now we're done with the calculus. Now it's just a matter of rearranging, trying to group my dy dx terms or collect my dy dx terms together on the same side. I could factor that dy dx out, divide. I did a little bit of cleanup, but if it's screw response, it could be any variation. I just wanted to have us practice the cleanup just in case on the multiple choice AP question, you're trying to match it to the reduced version answer choice. Okay, let me just shift the attention to the homework from last night, or the one that you just did, because I didn't quite go over how to find the second derivative. So this is number 47. If you want to follow along with me here, 47 from last night's homework. So the first part, first derivative, that's not a problem, like finding y prime. X squared plus y squared equals 4. We find the derivative, we do power rule. We keep track of our dy dx there. We solve for dy dx equals negative 2x over 2y. The 2's cancel out, so dy dx is just negative x over y. Okay, so that's the first part. Okay, that's first derivative. But if I want to find the second derivative, guess what we have to involve here if I want to find the second derivative from here? Quotient rule and implicit as well, because I gotta take care of that y. So let's go through the process there. So I'm finding the derivative again, but I'm starting with this dy dx as my starting as my point here. Okay, so dy dx equals negative x over y. Right. So we said quotient rule. Okay, so quotient rule and implicit. Okay, so the notation that we use for second derivative is d2y over dx2. So I'm going to set up quotient rule here. Okay, so what's f prime going to be?
-1.
-1. G function, no changes. Back to F, which is negative X. G prime becomes
dy or dy.
all over
Y squared.
y squared, okay. Okay, so let me show you what the cleanup looks like, because we're done with the calculus. It's just a matter of how do we clean this up plus. Now, we may be asked to clean this up to represent our answer, guys. Go back. Okay, so we're back to, we want to represent our second derivative purely in terms of just x and y. So what can I replace dy dx with?
Negative x.
Yeah, negative x over. All right, so the calculus is done. We're just trying to get this as cleaned up as possible. Now it's going to produce a complex fraction. So let's see here. All right, so if I do a common denominator here, my common denominator will be y. So let's see, d2y. Common denominator is y, so I just step away for a moment just to take care of this part here. My common denominator is y. Balance my fraction here. My denominator is missing a y, so multiply the top by y as well. So I get negative y squared. This is fine. I can keep that x squared there. So d2y. So dividing by a fraction is the same thing as multiplying by its reciprocal. Merge those together, I get negative y squared minus x squared all over y cubed. But we can actually go one step further. If you saw this on the multiple choice question on AP exam, they're going to reduce it even further. What can I replace this negative y squared minus x squared with? Well, actually, there's okay, right, but there's actually something that problems like to do here. They want to involve the original equation somehow to make this even simpler looking. Do you see a substitution that is possible?
Negative 1 and 4.
Yeah, so here I can get this. If I distribute negative x squared, negative through, I get negative x squared minus y squared equals negative 4. And so that's the substitution there. So just be aware of that. I mean, if it was pure response, any of these answers are acceptable. But if it's multiple choice, just know that they may work all the way down to here, and you want to be able to know how to get there, right? So you're cleaning, you're replacing all your dy dx in terms of y, and especially with the second derivative, there's that ability sometimes to work in the original equation and get it down to even simpler form.
But this is the derivative, not the original function, right? Like,
right, but it's a suitable substitution, right? Because negative x squared minus x squared is the same thing as negative 4. So it's suitable, right? I'm still making a 1-for-1 relationship. But yeah, but this technically this is the second derivative. Right? I mean, it looks different than this, but if these are equivalent, then I can make that substitution. Okay, any questions here?
What if you have an x and a y value, but it doesn't, like, let's just say you're on to find derivative of a random x and y, but what if it doesn't equal -4 in the numerator? Or does it always equal?
It may not always equal, but typically, with the style of these problems, they tend to work out where that second derivative matches the first. Now, again, I want to say that, for sphere response, this is perfectly fine. If they ask you to represent your derivative purely in terms of x and y, any of these options are fine. But if it's multiple choice, I just want you to be able to know how to get to this answer choice if you're stuck here. Right. That's really the whole purpose of this, just so that we know how to get to this answer choice from here. Okay, so back to your packet here. Okay, try number 16, page 14. Now we have an extra step involved here. It says find the equation of the tangent line at a given point. So walk me through what are the big steps we have to go through here. Find the derivative, okay?
And the x
X and the
and the y.
to find the slope,
And slope.
Yeah.
And then
point slope. Good, yeah. So so every time we learn a new derivative process, you're going to be asked to find the tangent line equation. But this one feels more involved because your derivative is messier. You're going to need both the x and y value. Okay. All right, so try that. Oh, notation wise, I just want to point out something here. Typically, if it's a function, and if I want to find the derivative at 2, I would say f prime of 2, right? And then I would use that notation to represent the slope of a specific point on that curve. But if my equation was something like this, and I found my derivative, which is going to be implicit, there's going to be x's and y's. But I need, let's say I want to find the slope at a point, but the point requires both the x and y value. Typically, the notation is, because this only requires one number, you can just put parentheses. So if you use two numbers, they use a vertical line with the order pair here to indicate that I'm about to insert the order pair into this derivative equation because this has both the x and y value. And then here, let's say the derivative ends up being like 4/5. Then you can write it out this way. So I just want to point out some notation. How we represent a derivative that requires 2 points. So this is how they do it. Vertical line to indicate that I'm about to find the slope of an equation of a derivative that has both x and y as part of the slope formula. And then the only thing that can make this more complicated is sometimes they don't give you the y value. If they don't give you the y value, then you'll insert the 4 back into the original equation. Okay, after this, let's go to page 15 and see if we can try 20 through 22. So number 20, it says find the slope of the normal line. So what I would do is let's find the slope of the tangent line first. And then once you get that tangent line, then you can do opposite reciprocal to get to the slope of the normal line, right? So just focus on tangent line first. I think 20, you're gonna have to involve implicit and chain rule. Number 21, it's asking for the slope of a point that sits on the semicircle. So it'll help if we can build the equation of a circle. So circle equation is x minus h squared plus y minus k squared is r squared. Your h and k is the center of your circle, r is your radius. So if you can build your circle equation, then you can find the derivative, and then from the derivative, you can plug in 1 to get the slope, and then you can figure out the slope of that point that sits on the semicircle. Everybody okay with number 20? I'm sorry. I'm not going to require it, but I think it's, this is AP problem, so it's possible, yeah. But if you can think of it this way, that your circle equation is basically the Pythagorean theorem, and what Pythagorean theorem is, it's just basically a rearranging of that. So maybe that will help you connect with that circle equation a bit more. Yes. The other challenge of this problem is we need that circle equation so we can actually find the ordered pair. Because we need the ordered pair to get that y value, and we need that y value because the slope formula requires the y value. So that circle equation not only helps you get to the derivative, it helps you get to the ordered pair that you need to plug into the derivative to get the slope.
What's the process of elimination? Like, cause you can see it's a negative slope and then you can see that it's obviously less than one.
Yeah, I mean, if there's multiple choice on the test, you know, you can, especially on AP exam, right? Yeah, definitely use that. But if it's through response, then
Okay,
I wanted you to
Yeah.
be able to know that process.
Yeah.
I think it's good. I think it's good that you're using process elimination, but you always want to do that on multiple choice portion. Okay, and then let's finish up with 22. So product rule, implicit are both involved. Notice it's asking for value, plural values of dy dx. So that means there may be more than 1 point when y is 1. So insert 1 into the original equation to get your potentially 2 order pairs. And then the 2 order pairs can be plugged into the derivative equation to get 2 different slopes, right? Because you have, we're dealing with something that doesn't pass vertical line test. So you have overlapping points, and each point above each other may have a different slope depending on where it is on the curve. Okay, so your homework is just to finish up on 3.2. We'll start 3.3 next Thursday. I'll send out a reminder next Wednesday so that you know that I'll be checking homework on Thursday. All right, so come get your phones.
What if the homework buttons on derivative? Because like, I might not know how to do derivative. Of
We won't cover that till Thursday, though.
Yeah, but it's still homework.
Oh, it is.
Yeah.
Okay, so.
I mean, I can look at it.
It's becomes hard. But it becomes hard. There's only one thing though.
Guys, the calendar has 3.3. We didn't do 3.3, but the homework is all with implicit differentiation. So I didn't get 3.3, but I'll do that.
All the ones that are starting.
Oh, wait, 32.